So hello, welcome everyone to Spectral Geometry in the Clouds. This week it is our pleasure to listen to Charles Bordenave, who's going to talk to us about random perturbation of Toeplitz matrices. As usual, don't hesitate to ask any questions, whether by unmuting yourself or in the chat. I will relay the questions to the speaker. So yeah, Charles, the floor is yours.
Thank you, Laura. Thank you for the invitation. So I'm very happy to present joint work with my colleagues and friends in Toulouse, Mireille Capitaine and Chapon, which will be about Toeplitz matrices randomly perturbed by random matrices. So I think that most of you are not familiar really with random matrices, so I will more insist on the ideas and strategies of the kind of spectral argument that we have been developing. And so this paper is available on arXiv, and it is in fact an advanced paper of a previous paper with Mireille Capitaine that we did 10 years ago. So it's been a long collaboration. Okay, so let's move forward, and I have prepared for you a kind of introduction, which would be completely disconnected to the rest, but I think it's nice. So which will be about how do you study what a computer does when you ask to your computer what is the spectrum of a given matrix. Okay, so the matrices that we will play about today are Toeplitz matrices, which probably all of you know, but let's write them. So there are matrices which are constant on each diagonal, like that. And to each Toeplitz matrix, you can encode them in terms of a symbol, which I will denote by A, which is this finite Laurent series, where you put index by, you have to think of omega as being an element of the unit circle. And you define a function on the unit circle to C, whose coefficients are governed by the coefficients that you have put in your Toeplitz matrix. Okay, and so we will fix the symbol, so the function A, and consider my matrices depends on n as the dimension, and we will take n grow. So I will start with my favorite numerical experiment. Okay, so if you take, for example, the nilpotent matrix, okay, the usual one, so the symbol is simply the identity, right? So and I have asked to Python to compute for me the eigenvalues of this matrix when it is of size 10. Okay, so it's a very small dimensional matrix. Okay, so to fool a little bit the matrix, what I've done is I have taken this matrix T and I have composed it by a permutation. Okay, so this is exactly the matrix that I have asked Python to give me the eigenvalues. Okay, so and again, it's a 10 by 10 matrix. It is this one. So the reason I've made a random permutation, this permutation, it is because I don't want Python to detect that it is an upper triangular matrix. Okay, and so if I ask Python to the usual code that you use in Python to get eigenvalues, you will get this very interesting pictures of the eigenvalues. So he puts some eigenvalue at 0, and some of them, at least 4, are on this picture of modulus close to 1. Okay, and it's a very low dimensional matrix. Okay. And so you could try to repeat the same thing with a very large matrix now of size 2000. Okay, and again I take a permutation which I have taken random, and if you ask the same Python code to give you the eigenvalues of such matrix, it will give you this very nice disk circle with 1 point at 0. Okay, so these are very famous experiments, but I think, but I was very happy to find them. And you can play the same game by instead of taking a random permutation to permute the entries. I have tried to express this matrix, okay, this nilpotent matrix, in the Fourier basis. Okay, so this is my unitary basis, which is my Fourier basis. Okay, and I ask Python to give me the eigenvalues of ft f star. Okay, So here, of course, you have some numerical rounding problems which arrive, okay, which was not the case previously. And when you ask Python to compute the eigenvalues, for example, if you take n as being this number, you get the same picture, or most eigenvalues are on the unit circle, but there is a kind of outlier eigenvalue process which appears inside the unit disk, okay? And here I have taken n to be 2107, but if I would have taken 2108, you will get another pattern of outlier eigenvalues, pseudo eigenvalues, I should say, inside the unit disk. Okay? So this was for the simplest Toeplitz matrix that you can think of, so namely this nilpotent matrix. If you take a slightly more complicated symbols, like for example this one, which correspond to this matrix, you get the same picture, wrong picture, where all eigenvalues on this picture, if you ask the Python to what are the eigenvalues, here there is no need to hide the t inside by composing it by a permutation. And what the algorithm outputs, and you see that all eigenvalues, so the true eigenvalues, they align, they should be on this black line. But what does find Python is that most eigenvalues, they are very close to the image of A, of the unit circle by my symbol A, okay? And again, you can spot some things which could be thought as outliers. Okay, and you could repeat with more complicated symbols now, like this one, and you get another picture, but the same phenomena, some outlier eigenvalues, and most eigenvalues, they just stick to the image of the unit circle by your symbol A. And yes. Okay, so one of my personal motivations was to try to describe this phenomenon, okay, using some random matrix arguments. And an idea of that came to by reading at a very nice paper by von Neumann and Goldstein. It's a long paper written a long time ago, which was, as you know, von Neumann was involved in the Manhattan Project, and they were doing the first numerical computations with actual computers. And so, of course, they were computing, inverting and multiplying matrices. And at some point, they discuss in this paper the numerical rounding errors. And the authors suggested that maybe we could model numerical rounding errors by randomness. Okay, and this idea was very fruitful. And for example, you can interpret the smooth analysis of Spielmann and Teng, which was the smooth. Spielmann and Teng introduced this notion in the context of very closely related context of studying the simplex algorithm to solve linear programming problems. And the idea is that to try to understand what the performance of the algorithm that we use, that our computer use, we could take any deterministic problem that we have to solve and add a small noise matrix, okay, and see how what is the solution of the slightly perturbed deterministic, slightly perturbed, how does the algorithm works on a slightly perturbed variant of our deterministic problem. Okay, so for us, to be clear, we will study my Toeplitz matrix of dimension n, and n will go to infinity, and I will add some noise matrix. Okay, so I will not study directly what Python is really doing and the algorithm that they use to compute the eigenvalues, which of course, as you have seen, fail miserably here. But I will compute the real eigenvalues of my Toeplitz matrix slightly perturbed. Okay, and we are not the first to do that. There are many people did that including me, as I said, with Mireille a long time ago. Okay, so it has been a kind of fruitful line of work, which I will continue to develop today. Okay, do you have a question on the setting or? Okay, so I will first, so please close my introduction, and I will try to, now I will define the model and give you ideas of, try to sketch the main result. Okay, so what is our model? So I fix a given symbol, okay? So here I insist that my symbol is fixed and n will go to infinity. So for each, so R and S, R is a number of row of diagonal below non-zero rows, diagonals below the main diagonal, and S is a number of non-zero diagonal above the main diagonal. Okay, so these two numbers, like R and S, they are fixed forever. But what I will be interested in is my Toeplitz matrices where the dimension goes to infinity. Okay, so it's kind of random matrix type paradigm. And as I said, I consider the following random matrix. I take my Toeplitz matrix and I add a random matrix, okay, which is of norm of order 1, and I put to define the strength of the disorder, I put a parameter sigma n, okay, and this matrix yn, it is a matrix defined as follows. So it is IID in some unitary basis. Okay, so to be precise, UN is your favorite unitary matrix, for example, the identity or my Fourier basis or whatever, and in which randomness is expressed. And now my randomness in this basis is simply IID variable, which are centered and variance 1. Okay. And you have to rescale by square root n so that yn is a matrix of operator norm, say order 1. Okay, and so there are some technical assumptions that I will put under the carpet, which are satisfied for Gaussian, Rademacher, and most distribution that you can think of. But okay, if you're interested, you can go to and look at our paper. Okay, so but the most important assumption is that the noise is IID centered and unit variance in some given unitary basis, which I call UN. And now this sigma n, my noise will be converging as n to infinity to either a positive number or to 0, but in which case it should not be too small. Too small will mean that the logarithm of sigma n divided by n is 0. Converge to 0. So for example, exponential of minus square root n is fine, n power minus 100 is fine, but not exponential minus n. Okay, so the noise is small, it could be small, but not too small. Okay, and sigma, which will be this limit of sigma n, and it can be 0 or positive. Okay, so in the positive case, this matrix and this matrix, they are roughly of the same order. And when sigma n goes to infinity, this matrix has a norm much larger than this one. Okay, so that's the model. Just try to keep it in mind somewhere. It's called Mn. Okay, and usually I will remove, as we do in random matrices, I will remove the dependency in n. Okay, so except at sigma n, because this is a sequence, but don't be scared. Okay, and when we speak about circular Toeplitz matrices, there is one matrix which is never very far away, which is the associated circulant matrix. Okay, so a circulant matrix is it's a Toeplitz matrix, and the circulant matrix associated to my Toeplitz matrix T of A will be the same matrix. Okay, so the same main diagonals, but I add on the upper left, upper right, and lower left corner the coefficients which are missing, so that on each row the set of coefficients is constant. Okay, so the vectors of the A's the vectors of AK are just constant. The line are just the same up to a permutation in the circulant matrix. That's why it's called circulant matrix. And due to this invariance, the circulant matrix is diagonalizable in the Fourier basis, and its eigenvalues are simply the image of my symbol, of the root of unity by my symbol. So the first result that we should care about is, if you want to connect to the picture I showed you, is to try to understand what are the distribution of eigenvalues, okay? So how do we define that? You take a matrix of size n, and you associate a probability measure on the complex number, okay, which put a mass 1 over n to each eigenvalue counted by multiplicity. Okay, so it's a probability measure, and we call that the empirical distribution of eigenvalues. Okay, or sometimes the empirical spectral distribution, or the density of state, if you want. Okay, so just to be sure everyone agrees, so if we take the circulant matrix, we have seen that the eigenvalues are the image of the roots of unity by my symbol A. So the empirical distribution of eigenvalues of my circulant matrix puts 1 over n at all eigenvalues, which are in this case these numbers. Okay, and since the uniform measure on the root of unity converges to the uniform measure on the unit circle, weakly the law of my circulant matrices, as the dimension n goes to infinity, converge to the law of A of omega, where omega is uniform on the unit circle. Or if you are not probabilist, it's a push forward of the uniform measure on the unit circle by my symbol. Okay, so this one was easy to compute. Okay, people have also computed the limit spectral measure of the Toeplitz matrices. Okay, Tn. It's more complicated, and we will not use it. So I did not write the formula here, but it's just to mention that it is supported on algebraic curves, on some specific algebraic curves, which are inside the image of the unit disk by my symbol A. Okay, so for example, in my Toeplitz, in my nilpotent matrix, all eigenvalues mu of Tn is simply a Dirac mass at 0, because all eigenvalues are 0. And okay, so this is a point inside the image of the unit disk of my symbol, which was omega, the identity. Okay. Okay, so now a first result coming from random matrix theory is that if you remember, yeah, I take my perturbed matrix, my Toeplitz matrix perturbed by noise, its empirical distribution of eigenvalues. So there is some random association. It's almost surely convergence, weakly for the topology on measures, on probability measures, toward the limit measure, beta, which I call beta of sigma, which only depends on sigma, which was the limit of sigma n, so it can be 0 or positive. This measure beta sigma can be described if you know a little bit of free probability, but I will not use it here. So I just mentioned that the support of beta sigma was computed with Mireille a long time ago. And in particular, the support of this measure is exactly the set of points such that this integral, so you take the uniform measure, so d theta over 2 pi is a low density of the uniform measure of S1, and you look at the set of points such that when you take A of ei theta minus z minus 2 squared is larger than your noise level sigma minus 2, okay? And when sigma is 0, this should be infinite, okay? So this corresponds to the support of beta 0, which is simply the image of the unit circle by A. Okay, so this corresponds to this is in excellent agreement with the simulation I showed you at the beginning, that most eigenvalues were very close to the image of the unit circle by A. Okay, and this is true even when sigma n is like not exponentially small, but exponential minus square root n, so it's super small, but nevertheless, it's enough randomness to create this big instability of the spectrum. Okay, so this is not what I want to talk about today. Today, I want to study a more precise question, which is the study of the outliers. Okay, so here, François has found a super nice symbol with a very nice spectrum. Okay, and so the question we want to ask is the following. I want to study this point process of eigenvalues that you see here. So you fix a domain omega, which will be connected, okay, and which should not intersect the support beta sigma, but you can, which is what is in blue here, okay. And what we are interested in is the point process of eigenvalues inside my domain, okay. Okay, I want to understand the law of this rare eigenvalues that you see in this picture, which we call outliers. Okay, I did not mention the motivation to study Toeplitz matrices, except the one I mentioned about numerical analysis. But for example, Szeg and Vogel, they explain that these outlier eigenvalues, they are related to some resonance effect, but I cannot tell you more about it. But so there are some interest to, beyond what I've said before, there are some interest to study this kind of outlier eigenvalues. Okay. And it was found in the case where the noise is very small, like polynomially small, by Bazak and Zeitouni a few years ago. But to study this outlier, the winding number would play a key role. Okay, so what is the winding number of at Z of my symbol? So, which I will denote like that. It is this is a number of times that you see the A of S1, the image of the unit circle by A, circle around you. Okay, so in this case, this is simply the number of roots of A minus Z inside the unit disk minus the number of poles. Okay, and more graphically, here I've drawn a picture. So here you see 1 times it's a relative integer. You see 1 times the curve circle around you. Ici you see 2 times. Ici you see 1 times because it's 3 times, but there are 2 in opposite directions, and so on. Okay, so this is a winding number, and it will play a crucial role here. Okay, our first result, which is not super difficult, it's not the more advanced result that we have, is that in the region where the winding number is 0, okay, then, so remember, I fix a domain here, and the winding number is constant for all Z in this domain, okay? So if this common value is 0, then there will be no outliers, okay? So the point process of eigenvalues is just empty. There is no eigenvalues. Okay, so it's in good agreement with this simulation because here the winding number is 0, here it's 0, and here outside is 0, and you will see there is no outliers. Okay, but here in this region, the winding number is 1. Okay. So what's happening in this more complicated setting? I just sketch the main result, and then I will try to explain you what's hidden behind, and at the end I will give you a kind of more precise statement. But at this stage, let's just say that if the winding number of your region is non-zero, then there is some explicit non-zero random analytic function on your domain, okay, which I call phi, which depends on the variance, on the limit of the variance and the winding number, such that the domain, such that my point process of outlier eigenvalues converges to the 0 set of this analytic function. Okay, so and since it's non-zero, it's a discrete set, and that you can and there will be an explicit distribution for this random analytic function. Complicated, but explicit. Okay, so in principle, it gives you the law. So not in principle, but so we know what is the law of eigenvalues in any given domain asymptotically. Okay, so this random analytic function which encodes the eigenvalues, whose zero set encodes the eigenvalues of my limiting perturbed Toeplitz matrix, it will be a Gaussian, for example, it will be a Gaussian analytic function. If the winding number has absolute value 1, and for example, if the entries are, the noise is Gaussian, or if the orthogonal basis in which I express my noise is flat, for example, the Fourier basis, if the L infinity norm of the coefficient goes to 0. Okay, so in the Fourier case, whatever the nature of the noise that you put, in whatever the nature of the noise, if you perturb with if it's IID in the Fourier basis, then the distribution will be universal. But if you perturb with respect to the canonical basis, then the distribution here will depend on the statistics of the noise. It will be different if you started with a plus minus 1 random or a Gaussian, for example. Okay. Okay, I did not give you the explicit, if you can look at the paper to see what is this explicit random analytic function, but I can just give you, in the simplest of the simplest case, so my nilpotent matrix, whose symbol is the identity, the domain is the unit disk, and the covariance kernel of phi is simply given by k z omega 1 minus sigma square of k z omega, where k of z is the Bergman kernel. Okay, so this computation we did 10 years ago with Mireille. Okay. Okay, do you have... So now what I want to do is to try to explain you, I think the results I think are nice, but I want to try to explain some, I think, interesting spectral arguments which we use to get this kind of result. Okay. So the first idea, it's that of our method is that my Toeplitz matrices, they are we call it banded Toeplitz matrices, meaning that since R and S are fixed and the dimension grows, the size of the band remains fixed as the dimension grows. So my matrix has a lot of zeros. Okay, and as such, it is a small rank perturbation compared to the total dimension of the underlying space and to the circulant matrix. Okay, so my Toeplitz matrix, I can write as the circulant matrix minus what I have to add to get a circulant matrix. Okay, and I could write this matrix of size n. This one, it has a rank at most. Here you have S entries, and here you have R entries. So it has rank at most R plus S. And you can write this as a product of two matrices of size R plus S over N. Okay? So there are multiple choices to do that, but we have chosen this explicit choice. Okay. And so we see Toeplitz matrices as, even if they are very complicated, like the nilpotent matrix is super sensitive to noise, but it is extremely close to this circulant matrix with all one and just one at the bottom end, which this one is a normal matrix, which is diagonalizable in a unitary basis. Okay, here's the Fourier basis. Okay, so, and we will exploit, instead of doing our spectral argument, we will only do them on the circulant matrix. and then treat the Toeplitz matrix as a bounded rank perturbation of a very nice matrix, this circulant matrix. Okay, so the key point is that it is orthonormalizable in diagonalizable, sorry, in an orthonormal basis. Okay, so that was the kind of first step or first idea. Okay, now I come from random matrix theory, and so I knew beforehand that when you take a normal matrix like the circulant matrix and you perturb it randomly, the spectrum behaves very nicely. Okay, in the sense that there is no sensitivity analysis. So to be more precise, so I consider my the matrix I'm interested in, Toeplitz plus noise. I write it as circulant plus noise, which I call S, minus my finite rank. Okay, so S for stable. Okay, so this circulant plus noise is very easy to, not easy, but it's people working in random matrix theory know how to deal with such matrices. So, for example, the empirical distribution of these matrices converge to this a limit measure, which has an interpretation in terms of free probability theory. And it is also true that the spectrum, the set of the support of this measure, converge to the support of my limiting measure, which is again given by this formula. Okay, and as I said, that it is the resolvent, even if S is not a normal matrix. Okay, because the noise, this is a normal matrix, but this is a IID noise. Okay, so S is not a normal matrix, but since it is a perturbation of a normal matrix with IID noise, it inherits some regularity from the normality of C, and in particular, the resolvent of S is well conditioned, meaning that the norm is bounded away from the limiting support. Okay, which is completely false for the nilpotent matrix. And we can be much more precise than that. For example, if there is this nice phenomenon, that if you take, so again, my stable matrix is circulant plus noise. If you look at the resolvent of the circulant plus noise matrix, and you compare it to simply the resolvent of the circulant matrix, which is trivial, okay, to compute. Then if you fix it, the difference goes weakly to 0 when you are outside of the spectrum of S. Okay, meaning that if you take any sequence of vectors, phi and psi, the difference taken a scalar product with these vectors will go to 0. Okay, so I should have written phi n and psi n. Okay, and even much more, we can know much more. We can also compute the rate at which it goes to 0. It goes to 0 at rate square root n over sigma n. Okay, so sigma n is the level of noise, and square root n is square root of the dimension. Okay, and we call that the master field. Okay, in the paper, you will see why. Don't remember the notation, but I will repeat it a few times. So what we look at this difference between my resolvent of my stable matrix, my circulant matrix plus noise, minus the resolvent of the circulant matrix. Okay, so this is deterministic, this is random. I scale the difference by square root of sigma, square root n divided by sigma n, and I take it and I consider, I take this with, I compose it on the left and on the right by my matrices, which are of dimension n times r plus s. Okay, the nature of P and Q here doesn't matter, just their size. Okay, so if you want, I just fix a collection of vectors psi, phi, and psi k, and I look at the image of psi k tensor product psi l with respect to this matrix. Okay, and this converge as n goes to infinity. Okay, so I will come back to this proof, which is the main probabilistic part of the argument, but so I will take it for granted for the moment, is that this function, so it is a function from my domain in my complex domain, okay, omega, to the set of matrices. It is analytic, okay, and it converges as the dimension goes to infinity toward an explicit, non-degenerate, random matrix, analytic matrix valued function, which I call W. Okay, W is a function from omega to of m of r plus s of c. Okay, so it gives you the fluctuations due to noise of my circulant matrix of the resolvent of the circulant matrix perturbed with respect to the resolvent of the circulant matrix. Okay, so properly rescale, it converges to something explicit, random, non-degenerate, non-zero, which we'll tell you a bit more later. Okay, but before that, I want to finish in some sense the proof, at least the argument, the overview of the proof. Okay, so this was only a probabilistic ingredient that was needed. Okay, so now how does the proof go? So you remember I'm interested by the eigenvalues of my matrix M, which is now I come back to my problem, my Toeplitz matrix plus noise, okay, which I write as my matrix S minus the finite rank perturbation, okay? So am I interested in the zeros of this function? Okay, the characteristic polynomial. So I write this as, I say that M is S minus PQ, so I am interested in the zeros of this function in my domain. I know that from what I said earlier, that this S has no eigenvalue in my domain. There is no outliers for S, okay? So I can factorize by this and make appear, and you will see Z minus S minus 1, the resolvent of S, which will appear. Okay, so since I'm interested in the zeros of that, and I know that this is not zero, I'm interested in the zeros of that. Okay, and now comes the a great trick, which was first used in random matrix theory by Raj Rao and Florent Benaï-Georges, is to use the Sylvester identity, which says that the determinant of I plus AB is the same as the determinant of I plus BA, when A and B are matrices so that they can be multiplied. Okay, so this identity, which is called the Sylvester identity, is super powerful in our context because now here I have the determinant, a huge determinant of an n by n matrix. I use Sylvester and I get the determinant of this matrix. Okay, so this was my matrix A and this was B. Okay, so you get the determinant of this matrix where, okay, so which is now a determinant of fixed dimension of size R plus S. Okay, so of course, this depends on n, this depends on n, this depends on n. But now you only have to understand the limit of this resolvent composed by my matrix Q, my rectangular matrices Q and P. Okay, so to summarize, my eigenvalues, my outlier eigenvalues, they are the zeros of this function. So you see something which starts to look like my master field. Okay, which my master field was the difference between my resolvent of my matrix S and the resolvent matrix, my circulant matrix, composed by my matrices Q and P and properly normalized. Okay, so I replace, so this was the same line that's the one line before. I want to make appear my master field, and I get this expression. So this is a deterministic expression, which depends on n. This is my circulant matrix. These are my matrix Q and P, and this is my matrix field, which is normalized by something which is very small. Okay, but this guy, I know that it converges as n goes to infinity to a random analytic valued matrices of size R plus S. Okay, And now what we do is we develop the determinant. Okay, so you all know that the determinant of A plus B is the determinant of A plus trace of the cofactor matrix, which I think in English is called adjugate matrix of A times B plus a rest, okay, which is a derivative of the determinant of A plus B with respect to B. This is this. Okay, so you know this formula, and in fact, it generalizes, and you can extend it to any order, and you get that the determinant of A plus B is equal to the sum of the trace of adjugate matrix of order K. So the adjugate matrix of order K is indexed by the set of K tuple of indices from going from 1 to n, okay? And for each subset of order K, so this is a subset of size K, the adjugate matrix is simply, when you take two such subsets, you take the determinant of the matrix A restricted to this subset of size K. Okay, and you compose it with the case outer product of the matrix B. Okay, so the outer product of order 0 is simply 1. The outer product of order 1 is simply the identity, and the outer product of order K lives in the exterior algebra. So sorry, it's lambda. So I should have written lambda K of Cn. Okay, lambda K of Cn, yes. And it is defined using the usual notation for outer algebra as lambda K of B is taken of this vector is simply the image of each of these vectors by B. Okay? So you have a complete description of the development of the determinant without surprise. Okay. Okay. So now I can use this knowledge to do my exercise and to apply it to my problem. Okay. So my ratio of determinants is given by, so this is the same line than before, this matrix plus my noise. Okay. I develop the determinant, so I call that Kn. So it's a determinant of Kn plus I've just simply written down my complicated expression with the adjugate matrix of any order. Okay, from 1 to R plus S. If I apply Sylvester back to this expression, this determinant, I can interpret it's equal to the ratio of the determinant between the Toeplitz matrix and the circulant matrix. And now there is a very nice theorem by Szeg, which is called the strong Szeg theorem, which was proved. So there is a weak Szeg theorem and the strong Szeg theorem, but the same Szeg proved, but there is 20 years of difference between the two proofs. And the strong Szeg theorem says that if the winding number is 0, then this ratio of determinant between Toeplitz and circulant converge to as a limit expression, which I did not write, which is an explicit formula, which is non-zero. Okay, and also all these guys, they are of order 1 at most, and since this goes to 0, all this expression is of order 1. So that's why I say that our first result was not super hard to prove. It was that if the winding number is 0, then there will be no eigenvalues, no outlier eigenvalues, okay? Because this is non-zero, so it's bounded away from 0, and since this is small, there is no way that this whole expression can be equal to 0. So that was the expansion of the determinant in the winding number 0 case, okay? Which was corresponding when this ratio of determinant does not vanish as the dimension goes to infinity. Okay, so on the opposite, it will be completely the opposite. When you have a non-zero winding number, this ratio of determinant will go to 0 exponentially fast. Okay, so that's this slide. So I have just rewritten the same expression. Okay, my expansion. Okay, and I want to understand that. So I have to be more precise, and I cannot rely on Szeg anymore. We have to write our own Szeg theorem in this case. So the first thing we did is that my matrix Kn, which is here, depends on n because the circulant matrix depends on n and so on. But it is a matrix of fixed dimension, R plus S. Okay, so it converges to a limit matrix up to some exponentially small term. The perturbation is extremely small. And this matrix K of Z, I did not resist to the temptation to write the formula because I've hidden everywhere my formulas for a purpose because they are kind of complicated. So this one is one of the simplest, but you see that it is relatively involved. But K of Z is so you compose. So there is an identity. You compose, and on the left and on the right by these matrices, which do not depend, and then you have the integral over the unit circle of this matrix, where here you see your symbol appearing, and f of omega is simply the rank 1 matrix associated to omega, okay, of omega, omega star. Okay, so, and now comes a standard lemma, which you know for at least for k equal to 0 and k equal to 1, you know that the determinant of a matrix is non-zero if and only if it is invertible. Okay, so the dimension of the kernel is 0. You may also know that the cofactor matrix or adjugate matrix, whose entries are the determinants of the entries are the principal determinants. It is non-zero if and only if the dimension of the kernel is 0 or 1. Okay, and more generally, the case order adjugate is non-zero if and only if the dimension of the kernel is less than k. So now comes the algebraic component of our proof. It is that we have been able to, it took us some time to compute the dimension of the kernel of this terrible looking matrix, and it is exactly the winding number in absolute value. Okay, so it means that in this expansion, the first non-trivial term will correspond to k equal to the absolute value of the winding number, and you get this formula. And now you are, it's over. You have obtained this, that the dominant term is this expression. This goes to 0, but it's okay because you don't care because you are interested to solve 0 equal. So this is not 0, so you remove it. And now you remember that master field converge to something. And my theorem, I repeat it here. The function whose level sets describes the point process of zeros of outlier eigenvalues is simply the limits of that, which is a trace of the adjugate matrix of order the absolute value of the winding number, estimated at this complicated matrix K of Z. And now you take the delta's order outer product of my master field. Okay, and you see why it is not Gaussian, it is multilinear of order, the order of the master field, the order of the winding number. Okay, so I have a few minutes left. Okay, so the main, I come back to the main technical proof from a probabilistic point of view and unique, it was this convergence of my master field to a limit. Okay, so I will not give you the proof because it will be too complicated and probably not so interesting for this audience, but just the first line is simply that, so we have to look at the difference between my circulant matrix plus noise compared to its resolvent to the circulant matrix, resolvent of the circulant matrix. So we do a resolvent expansion, but you can prove it's almost surely converging. Okay, so we expand brutally the resolvent in terms of the resolvent of the circulant matrix plus all the remainder term that you get in the power series development when you use the resolvent identity, for example. Okay, and now you remember that why my noise is IID noise in some unitary basis, and you obtain an ugly formula for my master field. Okay, it's a sum indexed by k of a complicated expression with powers of my random matrix X times the deterministic matrix U, this deterministic matrix. And it turns out that all these terms, so this brutal decomposition was very brutal, but it was smart enough to capture an asymptotic independence. But all these terms in the development for each case, they are asymptotically independent. And you can compute, you can prove that they will be all Gaussian, except possibly the k equal to 1 k, which can play a different role. Okay, and so we developed some, we have to prove that all of these terms, they converge to, we have to prove a kind of central limits theorem for this trace of products of random matrices of general form. And then we have to cope with the issue that this is an infinite sum. And so you have some tightness to prove that the sum is tight. Okay. So now some conclusion. So in summary, so for our problem of Toeplitz, we have written the Toeplitz matrix as a small rank perturbation of a circulant matrix. Okay. And instead of working directly with the spectrum of the Toeplitz matrix, which is horrible to look at, because the left and right eigenvectors, they have a nearly zero overlap. So it's terrible to try to study spectrally directly the Toeplitz matrices. Instead, as a proxy, we have looked at a very nice matrix, a circulant matrix, which is normal, so very stable spectral structure, and use it as to explore the spectrum of my perturbed Toeplitz matrix. So, and there were two ingredients: the convergence of the matrix field, which was a probabilistic ingredient, okay, and which is completely separated in our proof from the algebraic ingredient, which is what is the first non-vanishing differential of my determinant map in my determinant expansion. And this is where the Wanning number in the example of Toeplitz matrices plays a role. Okay. So we have, so our strategy works in much more, in more general setting, at least when you have, as I said, when you have a normal matrix, a finite rank perturbation of such matrix, and a random matrix. Okay, and so this, for the probabilistic part, it's everything carries over in this setting, but the algebraic part, it's very model specific, where you have to understand the rank of my kernel matrix, which was this one in my example, which could be extremely dedicated to compute. And even in the case of Toeplitz matrices, our matrix K was complicated enough, and it took us several months to compute its kernel. So, but at least for okay, the method in principle can be extended. Okay, and also I didn't mention that, but you can use a similar method to describe the outlier eigenvectors. So the eigenvectors associated to the outlier eigenvalues, and they will be localized, and you can express them in terms of the resultant of the circulant matrix composed by my vector P, my matrices Q and P. So there are random perturbation of some deterministic object that you can describe easily. Okay, so some perspectives now. So as I said, nowhere in our proof the spectrum of the Toeplitz matrix itself played a role. Okay, and only the spectrum of the circulant matrix played a role. It would be, so if you unwrap the proof and look at it again, you will see that the proof collapse, and probably at the critical, what I call the critical case, where the noise decays exponentially fast. Okay, and there I believe that the spectrum, when alpha would go from 0 to 1, there you will see an interpolation regime between the spectrum of the actual Toeplitz matrix and the spectrum of my noisy Toeplitz matrix that I've been discussing so far. Okay, so I think it would be interesting, but the algebraic structure would be much more, much harder to understand. Because in my determinant expansion, all terms will matter. Okay, so I think also it would be interesting. So the noise, we did a kind of mean field noise. So the noise was completely IID in my favorite unitary basis. But it could be nice to consider noise, for example, which is itself bounded. For example, maybe the same noise, you only perturb you take a diagonal a bound perturbation, noise perturbation of the Toeplitz matrix, you will get completely different results, notably at the level of the convergence of the master field. And the same applies, for example, if you take a self-adjoint noise. For example, instead of taking just IID, you take a Wigner matrix, which is just IID up to the fact that Xij is Xji star. Okay. So there are many, the world of non-dimensional random matrices and matrices is it's a vast world with many nice phenomena. And so what we just been able to do are small rank perturbation of nice matrices, so normal matrices. It could be nice to try to study more, but more general matrices. But I think that we did a little bit of that with Mireille 10 years ago. But I think that it would be better to start with examples like Toeplitz matrices is very nice class of family of matrices with that we understand well. To start with another class of matrices which can be of interest in some application. I don't know. And the last comment. I'm pretty bad at numerical experiments, but it would be nice to compare as I said, when you, for example, you take in the Fourier basis, the nilpotent matrix, when you evolve n, you see a point process of outlier. It would be very nice to compare the empirical distribution of such object to the distribution that we get in our toy model and see how different they are. Okay, so I think that was my last slide. So thank you for your attention.
Thank you very much, Charles, for this talk. We have time for some questions now. So, of course, you can either unmute yourself and ask them directly or write them in the chat.
So the analytic function in your result, do you know what happens to it when you get close to the image of your circle?
Yeah. Okay, so you can, in the simplest example, it's simply the Bergman kernel. What was that? Yeah. So here, for example, when you take the nilpotent matrix, so you see that the kernel, so if sigma is 0, so the covariance structure is simply the Bergman kernel. And so it explodes when you are, so the density, the mean density, you have the number of outlier points, the random function explode on the boundary.
And do you know how fast it explodes?
Me, I don't, but I think that Bazak, Vogel, and Zaytouni in a paper they looked exactly at this question. But yeah, we didn't.
And so I was wondering also, so you called your function W, I think, the master field. Is there a reason for this name?
For this?
For the name?
Master field? It's because in a related problem in random matrix theory, there is something which is people used to call the master field. So since it's a kind of it's a field, so it's indexed by complex numbers in my domain. It's a matrix valued field, but it's a field anyway. And since it governs everything, we call it the master field. But okay. Yeah, one thing I didn't say that it's not that the master field. It's a good point because there are multiple choices. So even when I write that the Toeplitz matrix is a normal matrix plus some small rank perturbation, there are many ways to write. This decomposition is not unique. So, and for any such decomposition, you would get another matrix field, which will converge the same way, because at the level of convergence of matrix field, you don't see the difference. But you will get slightly different laws, and yeah. So it's not really a universal object in this sense.
Thanks, Laurent, for the question. Do we have other questions for Charles?
I have one.
Yes, go on.
You said at the end that eigenvectors are localized, and is there an intuition for this, or is it a common fact for outlier eigenvalues in random matrices?
No, not necessarily. I mean, outliers eigenvalues. So you look at. So I wrote the. Okay, so I wrote the Sylvester formula. So I could have said that. Okay, so the reason is that you. Let me see. So localized, I should have been more precise. So there will be, yes, because the P and Q, my perturbation PQ of my stable matrix, it has zeros everywhere except in the small corner. So the outlier eigenvectors, they will be supported around these points, around these indices. Most of their mass will be in a bounded neighborhood of these indices. And in random matrix theory, I mean, it's not that you know what local, I mean, they will be close to something that you understand at least, these outlier eigenvalues. So here there will be a bond, you will be able to express them in terms of expression like z minus s minus 1 times p, where z minus 1, z minus c minus 1 times p, for example. Okay, I could have been more precise, but yeah, it's not super difficult.
Thank you.
Thank you, Cyril. Do we have more questions?
Hello, I have a question. Hello, I'm Stéphane, Macher.
Yes.
Hello, Stéphane.
Charles, I have a question about the process, the random process you get. This is the zeros of this random function. Is it a determinantal point process? As a
yes. Okay. The answer is no. I mean, there is a classification of such the Gaussian analytic function whose zero set is determinantal. You can find it in the book by Virag, Hug, and Krishnapur.
Okay.
And none of this example, even the simplest example where of the nilpotent matrix, you don't get a determinantal process. In our first paper with Mireille in 2014, we gave an example of a slightly different kind of outlier process which was determinantal, but it was a very large rank perturbation in norm. But we were taking just as a basic, for example, my just IID noise, and we were taking a rank 1 perturbation, which was a very large norm, but was a left and right eigenvector were almost orthogonal. And by tuning the parameters correctly, you could get as a limit a determinantal point process.
Okay.
But it was more a coincidence, I would say.
Okay. Thank you.
Thank you, Stéphane. Do we have other questions for Charles? Well, I mean, there were definitely a good number. So let's thank Charles again for the talk today, and we'll reconvene next week at the same time for a talk by Luigi Provenzano with a title to be announced later. So thanks again, and see you next week.
Thank you.
Thank you.
Thank you again for the great talk, Charles.
Okay.
Bye-bye. Sorry, I need to run.
Okay. See you. Bye-bye.
Thank you.